Hello, everyone. Welcome to the 63rd Online Spintronics Seminar. It's my great pleasure to introduce our speaker today. Dr. Dali received his PhD at Institute of Physics, China in 2009. He then did 2 years of postdoc at Oak Ridge National Lab and 2 years postdoc at the University of Utah before he was promoted as a research assistant professor. He joined the faculty of North Carolina State University in 2017, is a recipient of 2020 DOE Early Career Award and 2020 Journal of Physics Materials Early Career Award. Dr. Sun's research interests are in spintronics and optoelectronics of organic semiconductors, magnetic thin films, and organic-inorganic hybrid perovskites. It includes the studies of organic spin valves, organic light-emitting diodes, hybrid perovskite optoelectronic spintronic devices, and their device physics. The Sun Research Group at North Carolina State University focuses on exploring novel routes for spin injection and detection, magnetic field effect, spin Hall effect, and their applications in moleculars, polymers, and newly emerged materials. Dr. Sun is one of the pioneers who launched the spintronic studies in hybrid perovskite materials. So without further ado, Dr. Sun, please go ahead with your talk.
Well, thanks for introductions. Hello, everyone, and good afternoon. And I really appreciate online spintronic seminar to provide such excellent opportunities that we can report or talk about our recent progress in the spintronic study in hybrid organic-inorganic perovskite materials. Well, traditionally, this materials was famous for the perovskite solar cell studies, right? So this the PCE efficiency for this perovskite material can be up to 25% back in 2019 already, even comparable with the silicon business. But instead, what we care is about spin-dependent features in these hybrid perovskite materials, like a spin Hall effect, spin of the coupling, and particularly for the Rashba state in such a low temperature solution process, the semiconductor materials. Well, my previous experience was in the organic spintronics, molecular spintronics. So that's why it's very natural for us to continue our spintronic studies in these hybrid semiconductors, in contrast to our previous work in organic semiconductors. Well, so the title, the talk we're talking about today is about the Rashba effect in the MAPB, like the mesoluline lead bromide single crystals. First of all, I want to acknowledge all my funding support from DOE and NSF and also from the state. This is a collaborative work between the 4 research groups. And so one research group, we're collaborating with Aram Amasian from my colleague at NC State. My student Zhenjie and Tony really contributed to this work. And all the optics measurement was performed in the Valley Vadani's group in Utah. And the theoretical work was supported by the Professor Julia Galli from University of Chicago. Well, so that's the outline for my talk today, including the introductions, our previous roadmap for exploring the large spin of coupling in the HIOP materials, and then also the motivation why we want to study the Rashba effect in hybrid perovskite using 3 different methods, like spin pumping, circular photogalvanic effect, and the second harmonic generations. Right? So let's give the first part about the basic introduction. So I guess everyone here is belongs to spintronics community. So the Rashba effect is pretty well known, typical spin-dependent features in crystals. If a crystal of possessing a large spin-off coupling and a possessing of inverse symmetry. So like in the bulk non-central symmetrical crystal or at the interfacially effect, it will introduce a splitting of the 2 spin separate towards opposite direction of the K space, and holding different spin polarizations with the opposite K values with momentum, so indicating spin momentum relations. This, if you look at it from the top electronic state, you see a forming 2 spin contours, internal contour like clockwise, and outside will be counterclockwise with all the spin positions really connected with momentum space. So in this case, usually it contains two contributions, two terms. One is the Rashba term with all the spin position direction in the one xy plane, and also you will have another term called the Rashba Just House effect. So here we're mainly focusing on the first term, the Rashba effect, defined by the Rashba parameters, called shift of the energy shift divided by the k values. Well, if usually people use this Rashba coefficient, the Rashba parameters in the unit EV astron to determine the Rashba effect in a crystal in semiconductors. Well, so why the Rashba effect is so interesting in the quantum materials? Actually, people realize if we're forming a typical Rashba state, whatever caused by interfacially or bulk Rashba effect, if you induce a spin current, a three-dimensional spin current Rashba state, you will generate a transverse electric field induced by the inverse Einstein effect or inverse Rashba Einstein effect. So it turns out this spin-to-charge conversion efficiency in a Rashba state is very efficient compared to the spin Hall effect in the heavy metals, like compared to the platinum or the tungsten or the titanium. So all these metals, so Rashba states act as very efficient spin-to-charge conversions. And also it can be also used as very efficient spin detectors and also spin current generators or emitters for multiple spintronics applications. If we consider like a conversion between the two-dimensional, like a two-dimensional charge current induced by Rashba effect can be described by a simple equation here, induced by three-dimensional spin diffusion current, cross product with spin positions, and this efficiency was defined by the coherent length called lambda IEE coherent length as the Rashba Einstein effect. And by estimating the lambda IEE coherent length, we can estimate the Rashba parameters in these typical materials. So that's actually, it's motivated lots of research group to fabricate or prepare more novel Rashba type of quantum materials for this efficient spin-to-charge conversion interconverters, like for the spintronics applications. So multiple typical Rashba states. The one typical Rashba state can be formed between the metal layers, like a bismuth silver, as reported by Nature Communication paper back to 2013. They observed a pretty high spin-to-charge conversion efficiency coefficient can be at room temperature, can be up to 0.3 nanometers, forming between the bismuth silver and 2D electron gas. Another typical 2D electron gas with exhibiting the Rashba effect is oxide heat structure, as typical LAO-STOs. And to demonstrate it back to 2016, at a low temperature, like 10 Kelvin, they observed very strong spin-to-charge coefficient up to 6 nanometers in such a typical LAO-STO oxide heat structures. Additionally, you can also form in the Rashba effect on the surface on top of the topological insulator. Typical topological insulator also have a topologic spin momentum correlation due to the Dirac point. But if you deposit a bismuth layer as a buffer layer on top, you're forming a combined Rashba and the topological surface state in these cases, and your spin-to-charge conversion efficiency can be tuned because of the Rashba state. Actually, that's one advantage for the Rashba state for the spintronic applications, because by tuning the streaming level of the Rashba state by applying a gate voltage, right, or maybe any electric field, the spin-to-charge conversion efficiency can be tuned from positive even to the negative as the controllable electronically tunable of spin-to-charge interconverters, which can be used for spintronics applications. So that's happened in the inorganic system and inorganic semiconductors and the metal system. So here we introduce our studies while including this Rashba effect inside the hybrid organic-inorganic perovskite materials. So this material has been usually understanding in the beginning was famous for the solar cell studies. can reach to very solar cell efficiency can be 25%. And since the first work back to 2014, 2013, the first solar cell studies in the hybrid perovskite, then everybody, all the research group, all the world have like a fever for the hybrid perovskite. They start to invent all kinds of different fabrication methods, co-deposition, spin coating with a low temperature solution process method into single crystal, into ferroelectric responses, for lasing actions, for LED light emitting diode, for the field effect transistor, photo transistors, and it's the one also for the transit pump probe spectroscopy because the acetones, photons, phonons interactions in such a hybrid perovskite structures, and also magnetic field effect. Well, that's really put this novel material into different area of the condensed matters. So, like you can see, that's probably not such a material can be used for any of this field so widely. But for me, if I'm looking at the low method for the hybrid perovskite hybrid, taking what else is missing? Of course, it's spintronics, right? The spintronics is our features that we care about is still missing in these hybrid perovskite applications. Well, that's very intuitive motivations. Why we want to have including hybrid perovskite for spintronics applications? Because the prediction of large Rashba effect, because of heavy metals of lead, of in such a hybrid crystal structure in the octahedral layers, that the lead induces spin coupling, and because inorganic hybrid structures induce symmetry breaking. By the DFT calculations, with back to 2014, people predict there might be a huge Rashba splitting effect in this photovoltaic materials, which have not been reported before. And later on, people even use the same concept to describe why the photo color efficiency is high in the Rashba materials, in the hybrid perovskite materials. The reason is forming the indirect band transition. Once you're forming indirect band transition due to Rashba effect, you're forming the acetones. The combination rate for the acetone will be reduced because the indirect transition, which is forbidden of the spin selectivity rules. So that's what cause your acetone diffusion carrier diffusion length to be extremely long and might be responsible for the high efficiency for solar cell. So let's say that make the connection between the Rashba effect also for the solar cell studies. Well, of course, if it's a Rashba effect itself can be also used for multiple spintronics applications. So that's theoretically work to trigger amount of a myriad of all kinds of DFT calculations for the examinated Rashba effect in different hybrid perovskite materials, in the ferroelectric responses, even the low dimension hybrid perovskite, which is the perovskite Rashba state, the parameters change the function of the dimensions with the 3D, quasi 2D with different quantum wave effect. They estimated the Rashba effect can be even up to like 3 eV astron at room temperature. So even the 3 eV astron is pretty large values already. But that's all until now, everything is still related to the theoretically predictions. And back to 2017, finally, the first paper report the joint Rashba splitting in the MAPP bromide single crystal using RPAS. Even the RPAS mapping is pretty weak, vigorous. They estimated at low temperature phase, at all for the MAPP bromide is also all weak. It's acting a Rashba state with large Rashba parameters up to 7 eV astron. At room temperature, the Rashba state can be observed up to 11 eV astrons. That's a huge number compared to the inorganic semiconductors or inorganic typical Rashba materials back to 2011. In the bismuth telluride iodine, the maximum Rashba state we observe is 3.8 eV astrons. Right? And even in the LaSTO, the 2D electron gas, typical Rashba 2D electron gas, is Rashba parameters only 0.2. So here, the observed by Rashba in an MAPB bromide single crystal, even in a cubic structure, they have 11 eV astron, orders magnitude higher. As this report received lots of attention to be experimentals and DFT calculations to further study this structurally large Rashba effect in hybrid perovskite. Well, then debate comes. Some research groups said, no, I'm even using the same RPAS results. I'm not able to observe the splitting bands in the conductive covalence band. There's no Rashba effect. And also for the DFT calculations, also there are many research groups repeat the DFT calculation. They said, actually, maybe your Rashba state you calculate from DFT is due to the error because your method using is not correct. The Rashba state by their estimations is only like a 0.4 plus minus 0.2. Basically, it's negligible. So that's two forces start to debate each other. One system say, yes, this is Rashba state, we observe by RPAS, no problem. But another group saying that, no, there's no Rashba state. We experimentally, we don't see second harmonic generations. DFT, we don't see any spin splitting state. And even more questionable is such for the cubic structure of MAPB bromide. What's a cubic structure? Cubic structure maintains the inversion symmetry. There's no absence of the symmetry. How would you able to observe Rashba effect in a cubic structure? It's really questionable for this field. Well, then we came in, we say, all right, that we wanted to study really, that's basically our motivations. We want to do a systematic investigation to confirm or validate it, whether this Rashba state really existed in the hybrid perovskite materials. Well, that's a question came, how you determine the Rashba state in one specific material? How many methods we can imagine? Of course, you can do DFT calculations, but this is theoretical predictions. You can do in the RPAS, but it turns out RPAS, most results cannot repeat the same results as in the PIL paper in 2017. Seems that RPAS is not a perfect way to study the splitting band in such an organic-inorganic single crystal by solution method. The third way, to using optical spectroscopy by measuring the transitions. So that one of the typical features of Rashba state is indirect transitions. If by the optical pump probe measurement, they can demonstrate indirect emissions or indirect band transitions, that indicates of existence of Rashba effect. But still, this method didn't tell you the spin momentum correlations. It means just a large delta E, which give you the splitting of energy, but not the momentum. So we believe the best way to address the Rashba effect in any materials, actually in the hybrid perovskite material, should be adjust the spin momentum relations by using spin pumping or circular photogalvanic effect. So that's basically the motivation of our work to examine the Rashba effect in the MAPB bromide single crystals. Well, before we really investigate the Rashba effect, as we said, the Rashba effect needs to be formed by satisfying two criteria. One is symmetry breaking, the inversion, the breaking, symmetry breaking. Second, you need to have strong spin-optic coupling. Yes, we say it contains lead, but then adding the lead in such a diluted hybrid structure didn't guarantee you have a strong spin-optic coupling. We had to study from the beginning to see whether we have such a strong spin-optic coupling with this system before we studied the Rashba effect. Well, so that's way back to 2015. So we studied the spin-optic coupling effect in hybrid perovskite materials using the magnetic field effect. We observed the photocurrent changes proportionally as a function of magnetic field forming a halogen shape. And this indicating a singulate electron hole pair formation and transition to the triplet electron hole pair due to intersystem crossing, because singulate had two spins of the opposite, the triplet has two spins to be correlated. This intersystem crossing between two electron hole pairs can be only caused by the delta G mechanism on this specific case. Because the electron hole has different G values, when you apply magnetic field, they have different spin processing speed. So then you're able to convert to a singlet configuration to the triplet configuration that will be responsible for the magnetic field effect we observe in the photocurrent, electroluminescence, and also the photoluminescence. That's delta G indicated the electron on the hole has different G values, indicating a strong spin-optic coupling interactions for these electrons. Then we further on, we realize this hybrid perovskite structure is very similar to the gallium arsenide. The gallium arsenide, due to spin-optic coupling, they're forming the splitting bands, they're forming the S state and the J state. Hybrid perovskite do exactly the same thing, but the reverse electronic structure, we form a J state in the conduction band, the S state in the bottom valence band. So this work performed by the Salah-Lee's group in Utah, using our material, the MMPP bromide iodine material, chloride materials, is showing using a circulated polarized excitation, we're able to inject spin current into this band, into these materials, and by applying magnetic field, you see very nice persistence of spin persistence. You can measure the G values of holes, you can measure G value of the electrons. We're showing a huge, really precisely determine the delta G between two electrons, two particles, indicating a strong spin-optic coupling formation in such a hybrid perovskite structures. So then for the back to 2019, we use the same materials using a spin-off configurations. We're able to observe very nicely magnetoresistance using the typical MR responses, the spin diffusion at a low temperature. Even we have a lead as such a strong spin-optic coupling system, the spin diffusion energy can be up to 200 nanometers at 10K. By applying a vertical magnetic field, we see obviously the Henle persistence indicating the formation or injection of spin line carrier into MAPP bromide space layer. By measuring the weight, we can detect the spin diffusion length at 1 nanosecond and 10 Kelvin. So that came to the same, conjugated to our previous results, how a material has such a strong spin-optic coupling, right? Spin hole physics, the intersystem crossing. Meanwhile, we have a decent spin relaxation time. It's supposed to be inverse proportional, inverse correlation, but now they both existed in one materials. So that gave us the hypothesis, maybe there's another effect dominating the spin-dependent phenomena here. That's the way hypothesis, the Rashba effect, plays an important role here. Well, so that gave us the motivation to further study the Rashba effect in the hybrid perovskite materials using 3 different methods, using spin pumping, circular photogalvanic effect, and the second harmonic generations. Well, first of all, we try the spin pumping method in the polycrystalline thin film. We're doing in a single crystal, we're using a subject, we spin coating the MAPP bromide thin film, solution process, deposit nickel ion on top, forming a bilayer structure, shine the microwave, introduce spin wave in the ferromagnet, inject spin current into the hybrid perovskite materials. If our hypothesis is correct, you may form in the inverse spin hole responses from both contributions, also the surface contribution from which can be attributed to Rashba interface. By measuring the FMR responses, we see a clearly increased damping factors, indicating by the spin pumping method works, we really inject spin current into hybrid perovskite materials, even in the solution process, polycrystalline thin film, we still succeed to inject spin current, and we are able to measure a typical ISHE responses, and which reverse the sign when the magnetic field is reversed. There's a post ISHE responses using the microsecond range, give us a pretty strong signal indicating there is a spin to charge conversion happen in hybrid perovskite materials. But that's for the MAPP bromide. And we also do the multiple thin film to study their spin-to-charge conversion efficiencies and also calculate the spin hole angles, demonstrating their different spin-up coupling strengths. Surprisingly, we found even for all the hybrid perovskite, which is supposedly the spin-optic coupling is only dominated by the lead, the spin-to-charge conversion efficiencies change from negative to the positive, from small value to the higher values in MEPB bromide, even comparable with the platinum, the spin hole angles, like a spin-to-charge conversions. But here it's only lead, it's diluted lead in the octahedral layers. The acting a strong spin of the coupling like behavior like a platinum. This gives us really indicated why it happened. Is it due to the bulk effect or due to the surface dominated effect, which can be attributed to Rashba effect? So then we do the thickness dependent to further study the spin-to-charge conversion efficiency and function of thickness up to 300 nanometers. We found, surprisingly, we see the spin-to-charge conversion efficiency decay and saturate at high thickness. This is not the ordinary behavior, which is supposed to be not fit with spin pumping model. If we choose a typical C70, which is just like a fluorines, the spin hole angle to a spin-to-charge conversion efficiency should be increased and saturated at a higher thickness because because follow the tagging the d over 2 lambda expressions here. So it will saturate at a high thickness. What we observe is decay first and then saturated. So that gives us the motivations that the spin-to-charge conversions contains two parts. One is the surface state, which didn't change a function of thickness, which contributed to lambda ISHE, which is surface state, always be there. The second is contribute to the bulk effect, but the spin-to-charge conversion relations is negative. So it means negative spin hole angles, which is consistent with our measurement in the MAPB lead iodine, which without having strong Rashba state, we see a negative spin hole angles. That's validate our hypothesis is really this spin-to-charge conversion in the MAPB bromide thin film contain two contributions. One from bulk is negative contributions, and one from surface and is positive, large spin-to-charge conversions may be contributed as a Rashba effect. So in order to further to study the surface dominated effect, the simple way is you destroy the surface state. So we destroy the surface state by adding a lithium fluoride. It's not a copper. Usually in the inorganic, we add a copper transporting layer, right? The copper will be interacting with the MAPB bromide. So we're using lithium fluoride. The lithium fluoride provides a polar interface, change the surface electric field. If you change the surface electric field, potentially you also change the Rashba effect. It turns out after adding the lithium fluoride, the spin-to-charge conversion efficiency will significantly and statistically lower compared to the bare interface between the nickel and ferromagnet, between the MAPB bromide. This will come from the interface dominated this spin-to-charge conversion efficiencies can be understanding as the IE conversions, which is related with Rashba state. So then we can do our estimations. We observed Rashba speed ratings, the lambda IE coefficient up to 0.5 nanometers, compare the typical Rashba state in the bismuth silver, in the LAO, STO. It's comparable, but not that large. But if we calculated the Rashba parameters using effective mass and effective mass and mobility from these materials, the Rashba parameters in a polystyrene thin film is 0.3 EV astrons. It's not huge, but decent. But still, its orders magnitude lower than it was observed before, which is 11 EV astrons. Even it's lower, but it's still larger than LASTOs. So that's one hypothesis that, okay, that's because it's caused by zinc measure are part in a single crystal. We measure in a thin film. Of course, the single crystal showing how huge Rashba effect compared to the polycrystalline thin film. So the second study we're using, if you say so, let's study spin pumping effect in a single crystal to see what's the efficiencies. And we fabricate the single crystals provided by a Martin's group. We deposit nickel iron to measure the inverse spin responses in a single crystal. We see that we measure frequency dependence, power dependence. We see we observe clearly ISHE responses, which can contribute to the IE conversions point to the 0.015 nanometers efficiency. And we also we change the magnetic field to the in plane to outer plane with the Henry effect that we can ask by measuring the responses of ISHE function of angle. We're able to estimate the spin relaxation time on the surface between the ferromagnet and the single crystals. And we derive the single crystal spin relaxation time at room temperature at 189 picoseconds. Well, just a reminder, if it caused by pure spin optocoupling, people measure by from probe measurement at room temperature is only 4 picoseconds because of the lead. Contain the same heavy metal with the lead, MAPP bromide exhibiting a larger spin relaxation time, which is not expected. So that can be also contributed due to the formation of Rashba effect due to the Yakov-Pillay mechanism, because mobility is low, but then the spin relaxation time, which is inverse proportional. So that gives you higher spin relaxation time due to the DP modes in the 2D electron gas. So then we are able to estimate the Rashba parameter, which is still 0.3 EVS, even in a single crystal, which is consistent with our thin film. It's orders of magnitude smaller with the R-pass result. So until now, it seems that our results confirm that is negligible Rashba effect, will be smaller Rashba effect in such a cubic structures, which that we are standing on the negative side, right? But then spin-to-charge conversion still is harder to determine the Rashba effect because it's still in the indirect conversion happened later in the Rashba state. It's not related with the band structure directly. Well, so that's what we're using our second approach, secondary photogalvanic effect. This effect really connected with optical transition due to different helicity of the light illuminations. This method has been traditionally applied to investigate 2D electron gas topological insulators. By absorbing the circularly polarized light, the one direction spin will be popped out to the one band of subband. Because the spin momentum relations, that's group velocity for that spin-dependent photocarrier has a positive values. If you excited the same surface using left circularly polarized light, and you excited to the negative K space, give you opposite sign of photocurrent. So by tilting the angle, the incident angle from positive to negative, you will observe the oscillating of the photocurrent as a function of circular polarizations. That's directly evidence for the formation of a splitting state because everything is measured without electric field. The only electric field it have is because of momentum of the spin once excited by circular polarizations. And people use this math, actually the same author published in the PIL paper using published the PNAS publication in 2018. They demonstrated there is a possible splitting state in the MAPP ions. They say the Rashba circular photogalvanic effect. And the Utah's group, Valley Vadani's group also proved that in the two-dimensional hybrid perovskite, with the two-dimensional, of course, we have symmetry breaking due to the quantum wave effect. They're forming a typical Rashba effect. You're able to see continuous wave circular photogalvanic effect and transit circular photogalvanic effect give you terahertz emissions. But again, this is two materials, it's not MAPP bromide. As we said in the first report, the Rashba state was demonstrated in MAPP bromide. There is a missing evidence to the CPGE responses in MAPB bromide 3. So that's our motivation for our studies. We do exactly the same thing. We fabricate the best single crystal we can. We shine the cyclically polarized light by measuring the photocurrent as a function of cyclic polarizations. We see a very nicely oscillation of photocurrent as a function of cyclic polarizations. If we change the angle from positive incident angle to the negative incident angle, because spin polarization reverse, and the transverse photocurrent reverse too. The calculation can be seen here in the gray area if the L component, which is a linear photogalvanic component, which is not really spin dependent, always positive. If we reverse the angle from incident angle from positive to negative, we see the C component as a circularly photogalvanic component reverse sign as a directly evidence of the splitting state in such a surface hybrid perovskite materials. But again, here we only demonstrate the oscillating photocurrent according to different circular position illumination. That can be caused by chiralities. If somehow your single crystal forming chiral structure, of course you have different absorption coefficients, and the photocurrent you measure will be circularly dependent. So again, it's not a perfect effect to adjust the existent Rashba effect unless we're able to demonstrating the spin-dependent feature upon the circular polarizations. How to determine spin informations? We're using photo-induced ISHE effect. We add a platinum layer on top. It's a very thin platinum layer. And the same demonstrated by E.G. Saito's group back to 2010. The laser were able to penetrate the platinum, still have the CPG responses, but that photocurrent contains spin current. The spin current will diffuse into the platinum and convert in transverse electric field because of the high efficiency of the spin Hall angle in the platinum. And in the platinum, we're able, if the CPG still existed, and we also have the spin-dependent CPG responses, we should observe oscillating photocurrent in the platinum layer. Actually, it's true. We see the oscillating responses in the platinum layer even more pronounced. Orders the magnitude stronger than the CPG itself because of the platinum has a very strong spin Hall angle, really convert all the spin information into transverse electric field. If we reverse the angle, and we see the C term, the second the two sine 2 theta component, the circularly photogalvanic term really reverse sign from -90 to the positive 300. Directly demonstrate the spin current, spin-dependent photocurrent have been formed on the circular polarizations. Again, lots of inorganic semiconductor group will not satisfy with this statement because if you want to prove a spin current in any materials, show me Hanley responses. That's what we did. If we demonstrating the spin current injection into platinum by applying a vertical magnetic field, the spin information will start to process. And then your photocurrent responses should be decay as a function of magnetic field with the Lorentzian shape. By measuring the half-width maximum, you can get a spin reduction time, which is considered platinum and Rashba State together. If you apply magnetic field parallel to the spin polarization, which is supposed to be, then no Hanley responses should be expected. Well, we measure the same responses in the same structure by applying magnetic field. The D component, that's the background, the photocurrent background, have no spin formations, showing the negligible magnetic field effect. But still a little bit just due to the magnetic field effect due to the singlet triplet interconversions, but that magnetic field effect is very small. But then we see a pronounced decay as the typical feature of the Hanley effect with the C component, which is circularly photo-dependent component, showing a decay at a high magnetic field. If you apply magnetic field parallel to spin orientations, no change of magnetic field have been observed. So that's really confirmed there is a spin-aligned photocurrent have been formed due to the circular light illuminations due to the Rashba effect. Well, until now, we demonstrated, yes, there is a spin-dependent photocurrent. By taking advantage of photo-induced ISHE effect, we are able to estimate it. The spin relaxation time can be up to 500 picosecond at room temperature. More or less roughly, this result is consistent with our previous spin pumping result, like 200 picosecond, demonstrating the existence of Rashba effect. Well, we can also do mapping. We can do the photo-induced ISHE across the whole crystals to study which part gives us a strong signal or uniformly, because the interfacing effect, probably we see uniform distributions. Actually, we found it's not. We're measuring the bulk photocurrent conductivity across the whole surface crystal, like 4 or 5 millimeter by 5 millimeters. At a certain spot, we see a higher photocurrent densities because of morphology, roughness, and the optical absorptions. But even normalized by the photoconductivities, we found the spin component showing a spatial resolved distributions across the whole surface. It's not uniform. Only on some certain point, this zoom in pictures around this area, in some certain spot, the Rashba, the photo-induced ISU respect is maximized. Only on certain spot, not the whole surface. So that gives us a hypothesis. Oh, that's the reason people didn't observe the Rashba effect in the same crystal, because this Rashba effect maybe is locally. In the bulk crystal, it's cubic. Of course, there's no Rashba effect. On the interface, you have a surface state, you may forming a Rashba state. However, our results showing that the surface Rashba state only exists in certain spot, have a local symmetry breaking. If you look at the optical image which we collect, it's very perfect single crystal by eyes. Under the microscope, you still see multiple domains, multiple twin clusters. There's still the same composition, but different structures. Even this pyramid contains local symmetry breakings. But that's just I saying that local symmetry breaking, right? Because it still contains the lead. There's no evidence to prove our hypothesis. That's the reason we asked the University of Utah Valley Vardinis group do the second harmonic generation measurement. Second harmonic generation, the SG is a multi-photon microscope to determine the crystal symmetry. If you focusing the laser to the bulk of single crystal, you will only observe third generation harmonics. It's indicating there's no symmetry breaking. Only when you're focusing on surface, you can see second harmonic generation due to inversion, absence inversion symmetry breaking, but a very weak signals. We do a scanning across the whole crystals. Such a huge crystals, only a certain spot, with a red spot showing the imaging, showing the symmetry breaking, the second harmonic generations. All the other areas, the green area is the third harmonic generations, and the photoluminescence without containing any information for the second harmonic generation didn't contain any symmetry breaking. So this validates our hypothesis as local symmetry breaking only form in a certain spot on the surface of single crystal with symmetry breakings. That's also explained why experimentally that by APAS measurement, you are not easy to see such a responses by the splitting band of Rashba state. Because maybe you're unlucky, you're focusing your laser in a spot which didn't have local symmetry breaking. In order to further prove our local Rashba state formation, we asked the University of Chicago with Professor Julia Galli's group to do the DFT calculations. We found even the bulk material is the same. Still, the MAPB bond might contain same lead, same organic cations, depending on the surface of the terminations. The Rashba state can be changed significantly. By exposing more bromide, bromines, more lead on the surface, the terminations, the local terminations, determine the strength of Rashba effect. So that's answer the question, there the Rashba state exists in the MPP bromide single crystal? Yes, but locally. So that's give my summary for my talk. I introduced the Rashba effect, the hyperperovskite, why it's interesting for spintronics, and also it's a debate with the positive responses and negative responses. We confirm the Rashba state in hyperperovskite material using 3 techniques: spin pumping, CPGE, and photo-induced ISHE, and we also confirm the locally symmetry breaking on the surface single crystal by the second harmonic generation, support by the DFT calculations. So this summary concludes my talk. So there is the debate about the Rashba state in hyperperovskite. Yes. The reason is the Rashba state forming locally depending on termination of your single crystals. Both sides are correct. There is a Rashba state existing. There's also a possibility not able to observe Rashba state. That's because it's forming locally had to be detected by special resolved method like the second harmonic microscope or photo-induced ISHE effect, as we demonstrated here. Hopefully, our work will solve the controversy in this field and provide a new way to design hyperperovskite for large Rashba effect in this solution process semiconductors. So that concludes my talk. Thanks for your attention.
Thank you very much for this very interesting talk. So this talk is open for questions. If you have any questions, please use the raise hand function, or you can just send a private message to me. I'll read it for you. And if you're watching this on Twitch, feel free to just type your question in the chat box. I will read that. Let's see. Do we have any question? Maybe I can ask the first one. We use optical method to say that the Rashba state is not uniform, so it depends on the terminations. And it looks like there's only a very small areas in the very large crystal that shows the red spot with a very enhanced Rashba effect. But
yes.
When you do the spin pumping measurement, I suppose your sample is relatively large. So does that mean that your spin pumping measurement is actually significantly underestimation of the alpha R of the biggest, this average value kind of?
Yes, that's we propose that what we observe only like a 0.3 EV astrons, but that's just due to the underestimation of the whole surface. But probably all the spin pumping signal we observe from a single spot, which is alpha, may be really compatible with 11 EV astrons. But overall, average, so you just average by the whole area. That's why it's reduced.
How big is that red spot? I missed that figure. Is it micron size?
Yeah, the spot is in the 10 micron size.
10 micron size. So you cannot really do spin pumping, even though you know where the location is. You cannot pattern your sample to do spin pumping. Can you?
No, we can't. So that's why we had to using the second harmonic microscope. And even like photo-induced ISHE, we have the resolution somehow like 5 microns area. You see the red spot on the right corner, and really demonstrated that the formation that the spot contributed to the CPG responses.
I see. So my specific question is, after you use this optical method to identify that hotspot, are you able to do some other spin-to-charge conversion just on that spot? Some other type of measurement?
Well, I'm not sure whether I have such a spatially-resolved microscope or maybe really like by using photolithography, right? Detect the spin-to-charge conversion in that local spot. It's very challenging because these crystals are not like a graphene, like a 2D materials. They're very fragile to the solution, typical for acetones, which you need using the photolithographies.
I see.
So basically, we cannot do any photolithography or any nano patterning forming the electrode on this local spot. We can't.
I see. Just a suggestion, maybe you can try to do the spin of your torque measurement. You don't have to pattern that. You can apply a large current and just use optical technique to measure the local response.
That will be excellent ideas. That yes, we haven't tried, but I really appreciate this excellent idea that we can try probably later.
Great. Do you have any other suggestions? Kirill, please go ahead with the question.
Yes, thank you for the interesting talk. So I noticed in different figures that you showed, the band gaps were very different. Does that depend on the halogen ion?
Yeah, that's depending the terminations of the organic ligand and the lead exposure, the interminations. So that's which is a simulation. That's the DFT simulation to different termination with the exposure with the bromine or maybe lead or the lead bromines or maybe more. Even we can see like water absorptions on the surface. That's a dramatically change electrical structures of your Rashba state.
Yeah, but close to the beginning of your talk, there were also some with a fraction of an EV band gap, if I remember correctly. So that was a.
Let's see. Do you mean this one?
Slide 8, for example. Yeah.
Slide 8. Yeah, this one.
Yeah, you were right on it.
Yeah.
Yeah. So here it's just a couple tenths of an EV, right? So it's a different ligand.
So that's the DFT calculation, which we actually have lots of discussion with the Jack, Professor Evans about these calculations. He shows a very large Rashba effect by the calculation, but some other groups using different the DFT calculations, they demonstrate the Rashba splitting is negligibly small. So I wanted to comment for that why is it have different between different materials or different method using DFT calculations. So probably that's the different way to calculate these electronic structures. Typically, I was thinking it's related with the orientation of organic ligands, because once organic ligands do the relaxation, they will change the lattice. So by different relaxation rate of organic ligands during the calculations, your symmetry breaking will be destroyed, and you will have different electronic structures even for Rashba states.
So here in this picture, is this also for the surface?
No, that's for the bulk.
But for the bulk, doesn't symmetry forbid Rashba splitting?
So that's what Professor he calculated. That's for MAPB lead iodine 3. At low temperature, it's a trigonal structure. It does have symmetry breaking. So for our calculations, MAPB bromide at room temperature, it's a cubic. So that's the difference. In the bulk, we don't have a symmetry breaking.
Mm-hmm. Okay, thank you.
Thanks for the question.
Do you have any other question? I can ask another one. So I believe it was slide 29 when you did the Henle effect on the case of the kind of optical pumping, this inverse spin-Hall effect.
Yes.
Yeah, and so can you just remind me the Henle effect? This is still the Rashba effect, right? The spin is kind of generated at the interface, or is it generated in the bulk of the perovskite material? So basically, what I'm asking is the Henle effect related to spin defacing as it propagate.
Yeah.
So where does that take place? Is it taking place in the platinum, or is it taking place in the perovskite material?
So that's why we estimated this. You can see the mouse here. So the spin like the defacing happen at the combination in the platinum and probably also at the interface between the platinum MAPB bromide. First of all, the optical excitation happened within 5 nanometers if MAPB bromide because the CPG only happen at the interface. Once the photocurrent will be generated, the spin start to diffuse. It diffuse through the interface between the platinum and PB bromide single crystal, then inject into the platinum. So the Hanley effect, once we apply magnetic field, contains both regions. So that's why it should be like a 1/2 relations together. So what we measure the Hanley response here, spin relaxation time, I will define it as a total and effective spin relaxation time contains 2 interfaces.
I see. And on a related part, have you tried the Hanley effect when you apply BY, magnetic field in the Y direction? Will that behave the same as BZ?
We didn't try BY, but we tried BX. So BX means the magnetic field and spin position we generate the parallel.
Right.
And we don't see that that's the right corner figures. We don't see the significant change when they are parallel each other. Yeah.
Right. But if you do BY, do you expect the same as BZ?
I would expect it more or less will be the BZ directions. Yes, I would expect it to be, yeah, if that was still perpendicular to each other, right? Yes.
I see. Yeah. Thank you. Kirill, you have a question?
Yes, I wanted to ask whether it's possible to push holes into these Rashba bands or control them by electric field or gating.
That's the ultimate goal for demonstrating the Rashba effect in such a semiconductor materials. We want, usually in the oxide 2D electron gas, they're able to control the Rashba state by applying the gate voltage, right? Well, here, definitely, yes, we can apply gate voltage to tune the Fermi levels and of the interface, but I haven't tried that. But these are possibility. Once we form the Rashba state, the Fermi level can be tuned by gate voltage. And actually, this is a typical semiconductor materials. There's no reason why it doesn't work. But need time to prove it.
The fact that you have it kind of in spots, as you showed, is probably not a good thing for like transport measurements. You want to have a fairly uniform device, right?
Yeah.
Is there an idea on how to get there?
Yeah, of course. So the whole work here, so we just want to address the main debate why someone observed it, someone not, just because of local Rashba state. In the MAPB bromide, in a cubic structure. Actually, we have another materials that we have demonstrated before. We have here. So like a 2-dimensional hybrid perovskite. It is supposed to be forming a uniform surface state, even in the bulk Rashba state, because inherently it is possessing the Rashba splitting state without the locally distributions. So if we want to study the further gate tunable Rashba state, or maybe design a new larger Rashba effect, absolutely I will not choose the MAPB bromide because the cubic structure anyway. I will choosing the 2 dimensions, maybe quasi-dimensional perovskite. We have millions of these compounds that we can try, which is much better than MAPB bromide. The reason we choose MAPB bromide is want to adjust the key questions to solve the debates in the field.
Okay, yeah, thank you.
Yeah, thank you.
Great. Do you have another question? If not, we still have another opportunity to discuss with Dr. Sun after this. So let me check on Twitch. No, I think we're out of questions. So in that case, I just want to thank the speaker again and thank all of you for participating.